Hi guys, welcome to my video. This is the video 2 of the GD&T training sessions. Right, so some of the contents that we're going to go through today. Implied annotation. This is quite important. Do you need to put that 180 degrees box dimension or that 90 degrees box dimension? So we're going to go through some things that are implied on the drawing. We're going to go through the actual GD&T symbols, some of the symbol modifiers, the tolerance zones that you can use. I put a little slide there on why form control is required, what the tolerance and feature control frame, the tolerance or feature control frame is. In some standards it's called a tolerance control frame, some standards it's called a feature control frame. Theoretically exact dimensions, the box dimensions we're going to look at. And the importance of the datums in the tolerance control frame. The sequence of the datums in the control frame is very, very important, and we're going to go into why. Okay, so implied annotation. I've taken this from one of the British standards actually, or the ISO standards, because I thought this was quite a good explanation. And I've just made a comment at the bottom there that it must be clear what tolerance applies to all the features. So if someone's making a component, it's no good if they don't understand what tolerances are applied to that particular feature. And I think that's why one of the reasons why I prefer using box dimensions. You've got a feature control frame or tolerance control frame. The ASME allows box dimensions without that, and I think it's more confusing for people to actually understand what the tolerances are sometimes. Right, so basically when you've got something aligned or it's clear that the holes are at 90 degrees, you don't need to put 90 degrees box dimension in. If you've got a tolerance control frame with a positional tolerance in there, it's clear that it's exactly 90 degrees between the holes. I think reading this, one of the important things to know is most manufacturers will drill holes straight through the part unless you specify a depth. So some people put diameter 10 through, and the truth is you don't really need to put that word through in there, because generally speaking people will drill them holes straight through the job unless you specify otherwise. So it's quite important not to miss the depth of holes, otherwise the manufacturers might drill the hole straight through the part. So just make sure that's the intent, and that's number E there. Okay. Right, so I've taken this table from ISO 1101. It's quite a good table this, because it shows you what are form tolerances, what are orientation, location and run out. And one of the important things here is it tells you whether or not you need a datum. So one thing to note here is all the form tolerances at the top, they don't require datums. So your flatness doesn't have a datum in it. Your cylindricity doesn't have a datum in it. So I think that's the one of the most important things, to recognise on a drawing. Form tolerances, no datums. There's a little bit of confusion sometimes on the positional tolerance to whether you need datums or not. Now this table actually says yes or no. This is it's quite an old table this. Some of the standards change from year to year, and with some of these standards, I think there's a later version of this ISO 1101 now. I think there's a new version that came out in 2017. Now there's some new things in there, and I think they're probably a bit too new to use on drawings at the minute. It's probably good to leave them a good few years before using anything new on drawings. Otherwise manufacturers generally won't understand new symbols and things that you put on a drawing without looking at that standard. So I don't tend to use the latest standards. It's one of the reasons why I think that the ASME 1994 version is still used widely, because people understand it. So here we've got positional tolerance. When you're using BS 308 years ago, you didn't have to put datum A, B or C in the tolerance control frame. You can just say position, diameter, comma 3 or whatever, without having datums in there. Now in the later versions they recommend that you use at least one datum, And I think the reason is you need to know, you need to make sure that when you're going to drill a hole in something, you've got to clock the right face up first, and it really wants to be that face that you're drilling into. So you clock that face up so it's square to the machine before you drill them holes. So it's no good just them pattern of holes being relative to themselves. They usually want to be relative to the face that you're drilling in as well. So it's always really recommended to put that datum A in there as a very minimum. So that's what I would do nowadays. Okay, so this table can be used as a reference when you're doing your symbols and whether you need datums or not. Okay, so this is some of the modifiers that you can use, and this is taken from ISO 1101 as well. And some of them are very similar in the ASME. Some of them are very slightly different, but I think the meaning is very, very similar. So the important ones, you've got the theoretically exact dimension, which is the box dimension. It's where you draw something exact. There's no tolerance on that particular dimension. One that you might use quite often or shouldn't use quite often is the projected tolerance zone, which is the P in the circle, and we'll show how that works a bit later on. Another very common one, maximum material requirement. Least material requirement is not used very often, but it's obviously the opposite of maximum material requirement. And free state condition, the F in the circle, it's not used very often, but if you've got parts that aren't very rigid, you might want to use that symbol. Sometimes you can allow manufacturers to inspect components in their clamp state. Sometimes you want to inspect them in their free state. And depending on how they've clamped the parts, sometimes when you unclamp the part, the component can go out of flat, or it can move and things like this. So generally speaking, I would inspect most components in their free state, because that's how you're going to assemble them, unless they're very thin and you're going to clamp them on assembly in a similar way that the manufacturer is going to clamp them when they machine the components, for example. Okay, so we've got the all-round symbol. So it's just the circle on the corner of the arrow, which signifies the all-round. We've got an envelope requirement. So in this ISO standard, we can actually invoke the envelope requirement next to a particular dimension just by putting the E in a circle. And basically what that means is that particular dimension would then get read, very, very similar then to the ASME standard. It's very similar to the rule 1 of the ASME standard. It's basically the same. Right, then we've got the common zone modifier, CZ. You sometimes see that on the flatness of faces, where a component, where the face has been split up into multiple faces, for example. If you want to treat that surface as one surface, one zone, then you can put a common zone on the symbol, and we'll show an example of that later on. And the ones further down we don't tend to use very often. Okay, so these are the tolerance zones that you're allowed to use. Some of these you don't use very often, some of them you use all the time. The space between two lines or two parallel straight lines is used quite often. Space within a cylinder is used very often. Some of the other ones are not used quite so often, or the space within a circle is used quite often. Some of the other ones not quite so often. Okay, so why is form control required? Taking this example again from one of the ISO standards. So on this particular one, we do need form control. If this was ASME, you wouldn't need form control because we'd have an envelope of perfect form. But here we're using the ISO example where we need to put a cylindricity, for example, on this particular component to make sure it's straight and it's round. Here, we're basically measuring across 2 points. It's like measuring this this bar with a micrometer across point A, B and C, and you're getting the particular size there. Then particular 2-point measurements need to measure between the 24.9 and 25, which would then signify this component is okay. However, it won't signify the component is straight, the bar straight. So if you came to put this bar in a hole, it may not fit because it's not straight. With the ASME, you don't have to worry about this. It's taken by default. But with the ISO standards, you need to put something on there to make sure you control it well enough so it goes in the hole. Okay, so the tolerance control frame. I've just taken this from the internet, the piece in blue on the screen, and it just shows you what it looks like. We've seen this before already. So the first one is positional tolerance, then we've got the diameter symbol or cylindrical tolerance zone, which is normally what's used. It's normally a cylinder. We've got the tolerance, in this case I think it should be 5 thou. Then we've got the modifier, maximum material, and then your primary datum A, secondary datum B, and third datum C. One thing to note as well, generally speaking, the ASME standard uses dots as the decimal marker, and the ISO standard uses commas as the decimal marker. So if you think you don't know what a drawing's been done in accordance with, you looked all over the drawing, you still don't know. If it's got commas on there, it's usually the ISO standards. If it's got dots on all the dimensions, it's the ASME standard generally. Right, so some key things here. All box dimensions on a drawing need to go with a tolerance or feature control frame. That's when you work into the British standards or the ISO standards. But on the ASME, you don't need a tolerance control frame with box dimensions. So box dimensions on ASME can be used as gauge dimensions. They actually are used as gauge dimensions, but they can be used in other locations to do with features as well. You can use them on angles and a bit of all sorts. I think it's a bit more confusing using the ASME box dimensions when you've not got the tolerance control frame. I think it's sometimes harder to understand what the tolerance on that particular feature is. So I think I prefer the ISO standards in that regard. Sometimes you can split the datums with using A-B in a single box. So basically you're splitting the priority between them two datums evenly. And it's usually used when you want to use the center line of two diameters and you're machining something relative to the two ends of a part, for example. So if you've got an end diameter on one end of the part and another diameter on the other end of the part, and you want to machine something in the middle relative to them two diameters, you can split the datum priority by putting A-B as shown there in the middle, just there. So this would go in one of these boxes only. Okay, so theoretically exact dimensions. We've got an example here where we've got some holes that are machined into a plate, and it's just showing we've got datum A and datum B, and we're putting these holes in relative to face A and face B. So generally speaking, the box dimensions come from the faces that are in the tolerance control frame. Likewise here we've got an angularity on this one. We've got a box dimension, and then we've got this angle. So we're machining this angle, and this is the tolerance. So basically think about it as drawing this angle exactly 60 degrees, which is what this is saying. And then we've got an offset line this side and that side of this distance, and the actual surface needs to fall within that angle. So this is doing orientation. It's not doing the position of it, it's just doing the angle relative to this face. So in effect the angle could move along this line slightly. What this is doing is just controlling the angle accurately. On this particular case, normally the top face would be datum A, and then this would be B, and then this would be C. And we'll go into Y in a minute and exactly what this means. Right, so we've got this example here, and basically what this is trying to show is the actual tolerance zone here. It's not really just a circle, it's actually a cylinder. So we can see here we've got the top surface and we've got the bottom surface, and your cylinder is from the top to the bottom. So whatever we put here, say this was diameter 0,1, this would be here 0,1 here circle and 0,1 circle here, and the actual center line of the hole has to fall within that band. So the tolerance zone is actually a cylinder. So what this means really is if you've got a thicker part with the same tolerance on it, the thicker part's a lot more difficult to get right and to machine right, because if you're drilling a thicker part, your drill might wander off more. So you might have to use a different manufacturing method if you've got a tight tolerance here on a thicker part than you would on a thinner part. because the thinner part's a lot easier, because you know, the out of squareness matters a lot more on the thicker part. So in effect, you need more tolerance on the thicker part to use the same manufacturing method. So this is one of the reasons why the primary datum wants to be the face you're drilling into, or the opposite face, to make sure the hole's square to that face, and to make sure when you're bolting something up, the bolts will sit against the face, or the nut will sit against the face properly. Okay, so on this example, we're trying to explain which is the better sequence and why. So is it better on this example to have AB or BA? Now the truth is, GD&T, the datums are always treated at 90 degrees, exactly 90 degrees to each other. But the reality is the component itself may not be exactly 90 degrees. So this face may not be exactly 90 degrees to this face. And this is why the sequence is quite important, which we pick first and second, or first, second and third. Generally speaking, what you want to do is pick the biggest face or the longest face first. So in this example, this face is longer than this face. So to get the least error in where you're going to position the hole, this example would be better. So it should really be BA. So you want to pick this face first and then this face. So this sequence is better than this sequence. And I think an example with a longer part would have been even better to show. So this is that particular example. And you can see now the datums are treated exactly 90 degrees to each other, but the part may not be exactly 90 degrees. And it's the case of sometimes where people forget to tie up faces relative to themselves, or datums relative to themselves. So you might want to control the squareness of this face to this face if you're using this and this datum. Right, so on this example, if this component was a lot longer, you can see you know, the difference that would make. The amount of error you're going to get on a longer part is going to be a lot more, which is why you want to use the longest face first. So this example was better in my opinion than this example. So basically you're datuming this face of the component first and then this face. So basically your position's coming from this location here. A lot of manufacturers tend to split the difference, and what they actually do is put the hole in relative to this point here. So they half this error, but the reality is when you're using GD&T, the right way of doing it is to push the part up to where it stops, which would be this location here, and then you take the actual dimension from this location, not from this point here. And that's the way it should get inspected if you're going to CMM it, for example. Right, so we've got another example here. This is more of a common example where the face of the component is your primary datum. So we're positioning this feature here, position of tolerance, this feature here, relative to A, B, C. So we've got A first, which is the face, then we've got B, which is the longest face, and then we've got C, which is the slightly shorter face. So this is how I would position this particular hole. So here we've got diameter 0.02. So what that is it's a 0.02 here and a 0.02 at this location here, and the center has to fall within that tolerance. This is actually controlling the squareness to A as well, but what we're saying here is the squareness of this feature needs to be better than this tolerance. So we've got a squareness to A as well, which is better than what this would normally give. So we can add multiple symbols to the same features. This is giving you the example of what the part actually looks like and how it's actually set up relative to the datums. So generally speaking, it's when you push the part up and you push the part up and the part stops. So if you had a very, very flat edge and a very, very flat edge that was exactly 90 degrees to each other, you'd push the part in that direction, but you'd push it against this face first and then that face. So you push it up against this face and then you move it that way until it stops. And that would give you your datums. Right, so we've got some tolerance zones here. In this case, they're not diameters. And what this is showing basically is we can use different tolerances in one direction to the other direction. There's differences where these boxes are positioned. If the box is positioned on the end of the arrow of the feature, what it means is the center line of the feature rather than the face. So that's quite an important observation, and we'll go into that in more detail shortly. So what this is saying is the center line of the 7mm, so the center line of this pad in this direction. If I was to draw a line down here and draw a line down here, and the distance between this line and this line is this 0.3. The center line of this pad has to fall within that 0.3 zone. But likewise, they've changed it and they're doing a 0.1 zone in this way. What they're saying is it's more important this way than it is this way. Okay, so this is more of a common example. So we're putting some holes in something and you've got a positional tolerance of diameter 0.1. Again, this is not using the datums at the minute, so my recommendation would be to at least put a datum A, the face you're drilling into, but this is just trying to show you what the zone is. So if I was to draw this 30mm, these 30mm, so I'm going to draw these lines coming through here and through here, and where they cross, where the lines cross, you get a point at that point there, that point there. So if you draw a circle on that point, a circle on that point, and the circle is whatever's in this box, that's where the actual position of the hole has to fall. But you're drawing all of these at the same time. Yeah, so you're drawing all of these points at the same time. You're drawing all of these little circles that are comma 1 all at the same time, and the hole centers have to fall within these little diameters of comma 1 all at the same time. So it's controlling this pattern of holes relative to itself. And that's what it's trying to tell you here. Okay guys, thank you very much for watching the video. Don't forget to subscribe so you can make sure you don't miss the next one.